All right, welcome to ECE 165. This is going to be a lecture on an introduction to CMOS logic. So let's create a new subheading here called CMOS logic. Okay. Now, Boolean algebra represents information using ones and zeros. Okay. In CMOS logic, we map logic 1, I'll draw it as a proper 1 here, to the highest supply voltage we have in our system. We typically call this VDD. And logic 0, maybe I'll put a bar there through here to make sure that's not logic O, logic 0 to the lowest potential we have available in our system, typically ground or GND. So we can, using this mapping, if you will, we can construct logic gates out of transistors using our switch model. Okay, so using the switch model of a transistor, we can do this easily. Okay. For example, let's take a look at the most basic Boolean algebra building block we can think of, the inverter. Okay. We can draw this pictorially as follows. This is a typical schematic of an inverter gate. We can also, if we really want to be precise about things, we can draw a truth table. So when the input to this Boolean inverter is a 0, the output is, well, what do you know, a 1. And similarly, when the input is 1, the output is 0. Okay, so this will be on the final exam. Okay, so what we can do then is we can construct a model of how to actually build that inverter using transistors. Okay, so before we just assume that we have this magical element that when we introduce a logic 1 to it, it produces a logic 0 at the output. But how do we build that in the physical world? Well, we have to use transistors. So it turns out our switch model of our NMOS and PMOS devices is perfectly suited to doing this. Okay, so what we can do is construct the following circuit. Okay, so we have two transistors stacked in series. One is an NMOS, one is a PMOS device, and we connect their inputs together. We call this in. I'll use a solder dot here, and this is out. Okay. This, by the way, is the symbol for VDD that we'll use in this course, and this is the symbol for ground. Okay. So we can use our switch model that we introduced in the earlier part of this lecture and make sure that when input is 0, we get an output that is logic 1. Okay, so let's just go ahead and analyze that case. When in equals 0, we get the following circuit. So remember, we're going to essentially make switches out of our NMOS and PMOS transistors, and they are being activated by this input signal, which is equal to logic 0. Okay, now we said for an NMOS transistor, when its gate voltage is low or logic 0, then it is an open circuit. Okay, and for a PMOS transistor, when its gate voltage is low or 0, it is a short circuit. Okay, so I'll just draw a little arrow saying that is the output. Okay, so in this, or that this is the direction of the switch. So in this case, the output voltage is going to be what? Well, we have a switch connecting the output to VDD, which is of course equal to logic 1. So perfect. When the input was 0, we have a logic 1 at the output. Now similarly, when input is equal to logic 1, we get the following circuit model. In this case, the PMOS device is open. The NMOS device is closed. I'm running a little bit out of room here. In equals 1. That's trying to activate these two gate devices. So again, when when the gate of an NMOS device is high, or logic 1, then it is on, or in other words, its switch is closed. Okay. Similarly, the gate of a PMOS device, when it is 1 or high, that device is not on. So in other words, it's an open circuit. So in this case, the output voltage is connected to ground, which is of course logic 0. Okay, so what this means is that when the input is 1, we get a logic 0 at the output. So that's great. That's what an inverter is supposed to do. And indeed, that's exactly what it does. So what we just drew here models the logical behavior of a CMOS inverter. Later, we will characterize its speed, power consumption, etc. Okay, and that's going to be really, really important for the rest of the class. We want to build digital circuits, but we want them to build them to be good. You know, we want to actually be able to use them in a way that you know, offers the most bang for buck, or the most performance, or whatever it is that we're most interested in optimizing. Okay, so that was just an inverter. Let's take a look at a slightly more complicated logical gate. Let's try and look at the 2-input NAND gate. Okay, so the 2-input NAND gate looks something like this. We have inputs A, B, and output C. Okay, so what we're going to do is construct a truth table, A, B, and output C. Okay, so all the possible combinations of inputs and outputs in the truth table are here. What is the output C going to be? Okay, so when A and B are both 0, that means A and B is 0, so a NAND gate is the complement of an AND gate, so C will be 1. When either A or B are 0, then the output is also going to be 1. The output C will only be 0 when both A and B are both 1, which is A and B together, ANDed together is 1, and then the complement of that is, of course, 0. Okay, so we have our truth table. That's, again, not rocket science to build a truth table like this, but it actually does help to conceptualize how we're going to actually build our transistor level model for such a device. Okay, so what I'd like to say here is the goal of this exercise is to develop a network of NMOS and PMOS switches that set C, output C, to the correct VDD or GND level, depending, of course, on A and B. We also must avoid short circuiting VDD and ground. We don't ever want to connect VDD and ground together through switches. Then we just have short circuit current, and that's when things melt and blow up and so on and so forth. So we definitely want to avoid that situation. Okay, so what I'm going to do is I'm going to introduce some design guidelines to help us through logic synthesis. Okay, so let's take a look at these. These are static CMOS design guidelines. Okay. Step number 1 is NMOSs should only, oops, a very tall U, should only be used to pass logic zeros, and PMOSs only for logic ones. So it turns out there's a very good reason for this. I'm going to ask why. There's a very good reason for this, and I'd like you to think about this very carefully, and we'll get into this perhaps in a future class. Well, definitely actually in a future class. Okay, so that's guideline number 1. Guideline number 2 is the following basic structure can be used. Okay, so this is a structure that we're going to use throughout the rest of this course, so make sure to understand it very carefully. Okay, so we're going to say VDD is up here, VDD. What we're going to do is we're going to have some network of PMOSs, devices here, some network of NMOS devices down here. This is the output. NMOSs are connected to ground, and we have inputs. And it's possible there may be multiple inputs here. We're going to designate that with just a line through it to indicate that that could be potentially multiple inputs or outputs. Okay. Now, this is the basic structure. We said we only want PMOSs to pass logic ones, which means PMOSs should be connected to VDD. We call this the pull-up network, or PUN for short, no pun intended. Similarly, the NMOS devices should only be used to pass logic zeros, which means that the NMOS network should be connected to ground. So we call this the pull down network, or the PDN. Okay, so again, what we mean by this is that if a PMOS transistor in the pull-up network is going to be activated, it's going to be turned on, it's going to connect itself between VDD and the output, which means it's going to pull the output up to VDD. Now, hopefully, if we constructed our circuit properly, when that situation happens, no NMOS transistor in the pull-down network will be activated. Because if it were, one of those NMOS devices would turn on, it would connect the output to ground, and it would want to try and pull that output down to ground. Now, of course, we don't want the output being tried to be pulled in 2 different directions, and we don't know which direction it's going to go into. It's going to be short circuit condition. We really want to avoid that. So only one of the pulled up or pulled down networks will ever be on at once. And that is actually the third guideline, is only one of the pull up network or pull down network will be on at once. At once. And the reason for this is this prevents short circuit between VDD and ground. BTW in my shorthand means between, not by the way. All right, so in the previous slide, we discussed static CMOS design guidelines, and that's really all you need to know, and you can kind of figure out the rest later if you will. But I'm going to take it one step further and suggest some useful constructs that we're going to see time and time again throughout this course. Okay, and what I mean by useful constructs are basically just collections of gates that effectively produce specific behaviors here. Okay, so the first useful construct that we'll look at is the AND construct. Okay, the AND construct in NMOS transistors looks something like this. Okay, if you have two NMOS transistors in series, let's call this input A, this input B, then this construct is a short circuit. Sorry here, circuit. We'll just abbreviate this as short circuit when both A and B are equal to 1. Okay. Now we have a similar construct out of PMOS devices. With A and B at the gate here. Again, this is a short circuit when, in this case, A bar and B bar are both equal to 1. Okay, so that is our AND construct. We also have an OR construct that looks something like this. We have, in this case, we'll have two NMOS transistors in parallel here. So this is A, this is B. This is a short circuit when one of A or B is equal to 1, which makes sense. If A is equal to 1 but B isn't, the top transistor is going to short. The bottom transistor is still going to be open, but it doesn't matter. Those 2 points of the wires are connected together. Okay, and similarly for the PMOS, we have again a similar type of structure here, 2 PMOS devices in parallel. I should put the solder dots here to be extra precise. If this is A and B, this is a short circuit when one of A bar or B bar is equal to 1. Okay, so now that we have these useful constructs sorted out, let's go back to our NAND 2 example and complete it. Okay, so we started on this quest of trying to figure out how to build a 2-input NAND gate. By the way, when I say NAND 2, the latter number just refers to the number of inputs. As you can imagine, we can have a 3-input NAND gate. We would call that a NAND 3 type of device. Okay, so what we can do is let's actually go back and look at that truth table. Okay, so just for completeness, I'm just going to redraw it here. A, B, C 0001 1011, and this was 1110. Now in this case, I'm going to add 2 additional columns. Okay, I'm going to add a pull down network column and a pull up network column. Okay, so specifically, let's first look at the pull down network. At which point is the pull down network on? Well, the only time the pull down network is on is when the output is 0, right? So in this case, the pull down network will be on. In all the other cases, the pull down network is going to be off. Okay, and just by our design guidelines earlier, that means that the pull up network should be the opposite of this. But let's just make sure that that makes sense logically. The pull up network will only be on when the output should be 1. Okay, so that occurs in these cases here. And if the output is not 1, then it should be off. So indeed, the pull up network and the pull down network are complements of each other. Okay, so what we can now do is we have essentially a truth table for the pull up and the pull down networks. Let's figure out what logic function corresponds to each of these networks. Okay, so the pull down network should be on when, under what condition? The pull down network is on when, well, the output is 0. But if we look at the inputs, the pull down network is on when both A and B are equal to 1. Okay, so that looks like an AND construct that we showed on the previous slide. Similarly, the pull up network is on under what condition? Well, the pull up network is on when when one of A or B is 0. Okay, so we can write that down in Boolean algebra as when A bar or B bar is high. Okay, so when one of A or B is 0, or when one of A bar or B bar is equal to 1. Okay, so what this means is we effectively have these two logic functions from our useful constructs on our previous slide here. So now we can, by inspection, just draw our circuit. Okay, so this is VDD. The pull-up network is going to be one of those OR useful constructs. Solder dots. So this is A. That's B. And the pull-down network, let's take this output. This is output C here. The pull-down network is one of those AND useful constructs. So this is A, and this is B. Okay, so there you have it. That is our first slightly more complicated logic gate, at least more complicated than an inverter. So that's our pull-down network. This is our pull-up network. Okay, so that wasn't too hard. Let's write a few notes. Note 1. The pull-up network and pull-down network are duals of each other. And it's actually quite interesting. We can get into some graph theory and show how this, they really are duals and so on and so forth. Note number 2. This static CMOS method or design method with pull-up network and pull-up networks and pull-down networks can only implement inverting functions. Okay, so what do we mean by that? Well, what we mean is that if G is some function of inputs, that function has to be an inverting function. Okay, so what we mean by that is G can equal A and B inverted. That's an AND gate. G can be equal to A or B and C, all inverted, but it cannot be G is equal to A or B and C, for example. Okay, so one question is, well, how would we get this? Oops. Well, there's two methods. One is either we put an inverter after. You build the inverting function and then just put an inverter after. Or if we have access to inverted inputs, if we have access to A bar, for example, then perhaps we can actually recreate this function directly. But if we don't have access to any inverted inputs, then the only way to create this logical function is to put an inverter after your circuit. Okay, so that was one particular example, a NAND gate. Let's get a little bit more general and let's talk about how to implement arbitrary functions. In static CMOS. Okay, so again, I'm going to break this down into 2 steps, okay? And these are very difficult steps. I'm kidding. So, step 1 is realize the pull-down network by inspection. Okay, so you might say, well, that's not really a step. That's just saying do it. And bear with me. You know, we'll go through an example that will hopefully make this fairly clear. If you can't do it by inspection, you can look at the truth table, and this will help guide you to how to actually build this circuit. Okay. Step 2 is use De Morgan's theorem. And yes, I realize that some of you may have learned De Morgan's theorem more than 1 year ago and hoped that you never had to look at it again, but sorry, you'll have to look at it again now. Use De Morgan's theorem to manipulate the function to the point where the pull-up network can be implemented by inspection. Okay, so again, you might be thinking, well, Professor Mercier, that's not terribly useful. You're basically just telling us to do it. Bear with me. I think it will eventually make sense, particularly when we go through an example. Okay, so let's go through an example. F equals A or B and C, all inverted. Okay. So it turns out that step 1 is actually fairly easy once you wrap your head around it. Okay. So let's synthesize our pull down network. Okay, so we have A, or, B, and C. So we know an OR construct is 2 parallel transistors. The current can go through one path or the other. It doesn't really matter which one or both. Both will achieve the same function. Okay. Similarly, the AND construct is 2 series transistors. Okay, so if we want B and C, then we should put 2 transistors in series. Okay, so it turns out that drawing this by construction or by inspection is actually fairly straightforward. So we would have for the pull down network, again we're only using NMOS transistors. We put A on this side, or in parallel we'd have 2 transistors in series implementing B and C. And then this is the output F. Okay, so that's just looking at the formula by inspection, creating a pull down network. Okay, and again, just to emphasize, what we're doing here is we have an OR construct, so we put the two sets of transistors in series, and then we have an AND construct between B and C that we're putting together. Sorry, the A and the B and C are in parallel, and then the B and C are in series. Okay. All right, so that is the pull down network. The pull up network, we have to do a little bit of work. Okay, remember we have F equals A or B and C all barred. Okay, so what we're going to do is we're going to use De Morgan's theorem to simplify this formula a little bit. And what I'm going to do is I'm going to essentially take that top bar that's barring everything and bring it down into the formula. So this is equivalent to A bar or B and C barred. Okay, which is equal to A bar and B bar or C bar. Okay, so that's a direct application of De Morgan's theorem. Okay, so it turns out useful constructs for PMOS transistors are exactly the same as they are for NMOS transistors if the inputs are complemented. And in this case, the function has complemented inputs. Okay, so what we can do is exactly the same thing that we did for the pull down network where we do this by inspection. What we say is we have A and B or C, and all the inputs are barred here. Okay, and so what that means is that when we construct this, A has to be in series with B or C, and B or C are in parallel. Okay, so we can draw the circuit as follows. We have our 2 PMOS transistors representing B and C in parallel, going through an additional PMOS transistor representing A, and that's our output. Okay, so again, what we did is we just made sure to use De Morgan's theorem. We constructed our pull-up network essentially by inspection, by just looking at the formula and making sure that ANDs turn into series connections and ORs turn into parallel connections. Okay, so we can take this and put it together. All right, so let's just draw the whole circuit. I think it's hopefully fairly obvious about how we would put this together, but just for completeness, let's just go ahead and do it. So again, this is the pull-up network. So we have A, B, and C, and you'll notice I had C on the other side in the previous example. I'm flipping it here. It really doesn't matter. They're just in parallel. Logically, it's effectively the same thing. And then we go down to our pull-down network where we have our NMOS A over here, and then B and C are in series, B and C. And then the output here is F. Okay, now the beautiful thing of the beautiful thing of this course when you construct Boolean logic gates is when you're done, you can just check your answer and see if you're right. Okay, so let's verify. If A equals 1, what can we say? Well, if A equals 1, the pull down network is always on. And the pull up network is never activated. Okay, so that's good. If A is 1, then the output, the answer, is going to be 0 no matter what. It's A or B and C, all barred. And so if A is 1, it doesn't matter what B or C is, that sum is going to be equal to 1. That gets complemented, so the output is going to be 0. So this is correct, okay? Now let's just go through a specific example. We could go through the entire truth table if we wanted to, but let's just pick a particular example. ABC is equal to 0, 1, 0. In this case, what would happen? Well, A is 0, so this this part of the pull down network is off. B is on, so that's on, but C is off. So let's just draw it like this. So the pull down network's not on. Okay. On the pull up network, A is 0, so this PMOS transistor is on. B is 1, so this PMOS transistor is off, but C is 0, so this PMOS transistor is on. Okay, so this means that the pull down network is off, the pull up network is on, and yes, that's correct. And so we can kind of just, keep going. We can go through the whole truth table if we really want to, but effectively this just shows that, our equations or the way that we've constructed this CMOS gate is correct. So now that we have a little bit of a better understanding of the functional behavior of CMOS logic, let's get into a little bit more detail on how this these CMOS circuits would work, given that we know a little bit more about how the transistors themselves work. So let's again go back to look at the CMOS inverter. Okay, so the CMOS inverter, as we showed earlier, has an NMOS and a PMOS transistor. Something like this, V in over here, V out over here. Now what I'd like to do is I'd like to draw the voltage transfer curve. And this is always a good exercise for students in this class to make sure that they understand what's going on here, given the fact that we have a real transistor model. Okay, and what I'm going to do is within this curve, I'm going to describe the operation mode of an NMOS transistor and a PMOS transistor. Okay, now when Vin is large, we expect the PMOS device to be off and the NMOS device to be on. Okay, so we expect the curve to be something down over here. Now specifically, we expect the PMOS device is going to be in the cutoff regime, or more appropriately in the subthreshold regime. The NMOS device, we know it's on. The VGS of that NMOS device is very large. It's definitely larger than VT when Vin is very big, okay, provided that, of course, we're operating in above threshold. Now, the VDS of the transistor is actually going to be very small. V out is going to be close to 0, okay, and so what we say is that in this mode, the NMOS device is not saturated, but rather it's in the linear regime. Likewise, we can make a similar statement up here. In this case, the PMOS device is on and in the linear regime, whereas the NMOS device is off. Now, as we start to increase Vin a little bit more, we start to have the curve kind of start to pull down a little bit here. Okay, and so what happens is that here we're saying that the PMOS is turning, or rather the NMOS transistor is starting to turn on. So now let's say it's above the threshold voltage. VDS across that device is very large, and so we say the NMOS transistor is in the saturation regime, while the PMOS transistor is in the linear regime. Okay, and the opposite is true over here, and of course these curves have to meet hopefully somewhere in the middle here. We call this the threshold voltage, or the transition or the switching threshold of the inverter. So what we can say is over here we basically just get the opposite. The PMOS is in the linear, the PMOS is in the saturation mode, whereas the NMOS is in the linear mode. And then in this region over here, we basically say that both devices are on, both have some fairly good VDS across them, and so they're both in the saturation regime. So in this case, the inverter is really acting like an amplifier. Both the NMOS and the PMOS are both on. In fact, this is a good, or called sometimes a push-pull amplifier, where we basically get double the transconductance through the device because we're getting transconductance through the NMOS and the PMOS. But this is not an analog design class, but it's important to understand what region of operation that NMOS or these two transistors are working in. So we said that VM, we call this the inverter switching threshold. Okay, so question. How do we design VM to be, say, equal to VDD over 2? So the answer is, well, we don't have too many parameters available at our control as digital designers. So the only thing we can really do is adjust W over LP and W over LN until VM equals VDD over 2. Okay, and so that's the simple way to do it. So what that voltage transfer curve told us is that, we're building digital circuits. We want a 1 to be represented by VDD. We want a 0 to be represented by ground, but we actually live in an analog world, and that's not perfectly the case all the time. So this is why we have to talk about a topic called noise margin. And as I mentioned, logic 1 and 0 are not necessarily represented by exactly VDD and ground, but rather by ranges around these values. We use the following definitions to determine the margin with which we can operate. Okay, so let's imagine we have two inverters, one driving the other. And I'm going to just draw a little picture here. And this picture represents the range of possible values that this circuit could have. Okay, so this is ground at the bottom and VDD at the top here. Okay, so what we say is at the output of this inverter, we definitely want the VDD to be within some range up here to represent a logic 1, and the output to be within some range here to represent a logic 0. And in between here is no man's land. If the inverter is working properly, it will never get within this region. We call this the V out high, and this the V out low. Okay, so an output high voltage has to be at least as high as VOH, and an output low voltage has to be equal to or lower than VOL. Now we can draw a similar picture for this other inverter over here. Okay, now in this case for the input, we're going to make it a little bit more generous. We're going to say this is the no man's land for the input into this inverter. And we want to make sure that the input is at least higher than VIH, or V input high, in order to represent a logic 1, or lower than VIL in order to represent a logic 0. Okay, so basically what this allows us to do is set up a little bit of margin. Okay, so as long as our signal is output higher than VOH, then we can with good certainty ensure that it's larger than VIH with some noise margin on the high end here. Okay, and likewise we have some noise margin on the low end over here. Noise margin low. Okay, so we say VIH is the minimum high input. VIL is the maximum low input. VOH is the minimum high output. And VOL is the maximum low output. So we say the noise margin low is equal to VIL minus VOL, and the noise margin high is equal to VOH minus VIH. Okay, now there are varying definitions for how to define what VIL and VOL and so on are. This is one that we're going to use for the time being for the purposes of discussing how an inverter works. Again, I want to emphasize that there's many other ways that one could make these definitions, but this is, I think, a reasonably good one. So we're going to say that when the slope of this curve, and sorry, let me label the axes. We should never draw a plot without labeling the axes. The slope at which this curve is equal to -1, we're going to say is equal to VOH. Okay, and likewise over here, the slope where this is equal to -1, we're going to say this is VOL. Okay. And then we're going to drop down on the vertical axis over here and say that these points correspond to VIL and VIH. Okay. And so what we'd say is the region in here, this is the bad region. And what we mean by that is if the input falls here, we may not regenerate to a correct output or correct value at the output. Okay, so as I said, this is just one possible definition. VOL, VOH, sometimes is just the minimum or maximum possible output voltage. So just make sure that when you're discussing VOL, VOH, VIH, etc., that you just make sure that you're aware of what nomenclature is being used.